Hello everyone. In this video, I'm going to show the assembly of closed-loop CNC electronics. Since the customer had already purchased the components, and he had intended to wire the components himself, he later instead decided to have me assemble the components and mount them inside of an enclosure. Unfortunately, a few of the components got banged up in shipping. With the volume of components that were shipped, it might have been a better idea to ship them in a crate using a freight company. The spindle suffered the brunt of the damage. The tired and beat-up box containing the spindle shows what I feared. This is a very heavy 7.5 kilowatt spindle. The collet nut was jammed onto the threads at an angle, and every delicate attempt to remove the nut was unsuccessful. I didn't want to cause any more damage so that the customer could seek other more successful options, including insurance. The M18 strain relief cable nut assembly was also damaged, but I'll be using these nuts on the enclosure anyway, so I just replaced this one. The other boxes showed some damage as well, but the condition of the components were fine, with the exception of a ding or two, but we'll have no functional issues. By the way, consider clicking the like button if you are enjoying this content. It really does satisfy my serotonin levels, but also motivates me to make more of this content. Also consider subscribing to my channel. I make videos like this and bare metal microcontroller videos. You can see the customer did start wiring. I'm guessing after researching the depth of wiring and configuration, it was out of his comfort level. Transporting components with fasteners are subject to Murphy's Law. If the fastener can come loose, they will come loose. The rode, along with the suspension that cannot remove the fine harmonics that the rode creates, will cause screws and nuts to turn. Think of those vibration machines that sorts components. I do urge customers to assemble electronics and mechanical systems so they can have an intimate understanding of the overall machine in the event something goes wrong. They can know what to do, how to solve the problems, fix issues so that production is not halted for an extended period of time. But I know this is not possible for everyone, especially if near-term jobs or production is on the line. In most cases, it does make more sense for a technician to diagnose issues. Let me know what you think in the comments. One of the more time-consuming aspects of this type of job is finding the most appropriate arrangement for the components inside of the enclosure. There are so many electrical and space considerations. The most important consideration is the separation of delicate signals from the current heavy and coil-wired components like motors that emit interference. This interference can cause signals that are supposed to be either at a 0-volt level or a higher volt level like 5 volts or 24 volts. Interference can cause, say, a 0-volt level to go into a threshold voltage that the component doesn't know how to handle. You can solve this problem by arranging the components so that these signals are spatially separated or only intersect, rather than run in parallel with a higher current voltage wires. Additionally, shielding can be used. In these electronics, all cables for signals and motors are shielded. Other considerations for component arrangement is where panels are located around the enclosure, accessibility to various components for configuration and ease of wiring, and components' locations along the edges of the enclosure, like fans or vent holes. The controller needs to have access to the removable panel section of the enclosure so a USB or Ethernet cable can be plugged into the controller. I periodically need to insert the base of the electronics into the enclosure and then back out from time to time to get the components placed properly. When the base is inside of the enclosure, the perimeter around the base is very thin. Even my very thin fingers have trouble getting in there. If I'm going to do a lot of these, I'll need to either devise a better way for this exercise or plan better. Prior to assembling electronics inside of these enclosures, I made my own enclosures out of wood, and the planning was done in CAD, so there was no need for this kind of thing. And it was a lot lighter. Before fastening the components to the base, I try to think of anything else that will need to be added. This is where forethought is so important. There'll always be components that you forget to add, and that need drill holes. But drilling will leave a lot of metal debris, and that is not good with electrical components. This is a challenge I had during the build, and this is also why I create these videos in the first place. Manufacturers and assemblers doing repetitive jobs, or an assembly line, use process routing sheets. These sheets describe a number of steps in the most efficient order. Each step contains an operation description, the time it takes for the operation, and the equipment needed for the operation. My videos allow me to do all of the operations in the order I imagine is most efficient and easy. Then I chop up the video and rearrange the clips because the way I imagined it is totally wrong. This video shows these clips in the order I should have done things, with the exception of the bus bars added after the assembly of the power supplies. If you look really closely to some of the clips, you'll notice things out of place, but it all comes together nicely in the end. My intention with the orientation and placement of the drivers and power supplies was to keep the wiring as separate and neat as possible. Closed-loop drivers have a lot of connections. 6 connections for the motor encoder, 4 connections for the motor, 2 connections for the power supply, and 4 connections for the controller. The encoder and motor connections need to be routed to the removable enclosure panel. Because the encoder cables and the motor cables are routed in parallel with each other to reach their place on the machine, it is critically important for both of these cables to be shielded. You'll see later in the video how I terminate the shield. Fussing with screws and nuts for mounting a lot of these components can be frustrating and time-consuming, and also prone to getting loose with vibration. I may turn to using standoffs with clips instead, but the disparate hole sizes may not allow this. Also, a lot of these holes are grooves or they have open ends, so this may not be a possibility anyway. If you know a solution to this, leave me a comment. For the controller, I made spacers to bring the controller up to a level so that the USB and Ethernet connections on the controller can be accessed from the removable panel. These are the terminal blocks I referred to earlier that I added after the components were already assembled. It was difficult getting the drill into the area, and I needed to add protection to the other components so that metal chips didn't get into the electronics. Planning is essential. In a couple of the previous videos, I used zip ties and I got some concern in the comments, primarily with the cut ends. Cut ends of zip ties can be relatively sharp. To satiate you feisty folks out there, I also use UL-listed zip ties. For the inquisitive folks out there, the UL-listed zip ties are important for safety and strength for the application. The safety aspect relates to the material and harmful toxins emitted if burned or heated, or for the flammability or ignition properties of the material, or that they don't break down under exposure to certain chemicals. In a previous video, I soldered up a perf board with headers to provide for a more convenient way to connect ribbon cable. I really need to make a PCB for this, but the soldering isn't all that bad. This is for the connection from the controller to the drivers for the pulse and direction signals. To make the ribbon cables, my Knipex wrench comes in really handy. I probably talk about these wrenches in all of my recent videos. I do have a link in the description for these, which may give me a kickback, but I do truly love this wrench. I find myself purchasing a lot of the Knipex tools lately. It's good to see innovation in this sector of the tool industry. Many of these closed-loop drivers will label the power terminals as AC on each terminal, not describing the polarity. Those drivers will allow a DC or AC input, but be aware of the voltage level required for the AC if you decide to use that. Polarity is not shown on those drivers with the AC label, and I've found that the positive is near the motor coil connections as shown in the video, but be sure to confirm this with your driver as this may not be the case. Time to make the cables for the encoders with the connectors on each end of the cable. The number of wire ends to be soldered was 48, which included splaying out each end, twisting them together, soldering the connection hoping the ends would not come apart, heating heat shrink over the connections, hopefully not forgetting to add the heat shrink prior to soldering the end, and then adding a large heat shrink to the overall set of connections, also hoping not to forget the larger heat shrink prior to making all of those connections. This is one of the many times I needed to add the base of the electronics to the enclosure so I could mark the opening for the controller. Vevor or Vivor, not sure how to pronounce their name, seems to be a company that is providing a lot of industrial equipment these days. They did reach out to me to review one of their products. I selected a magnetic drill which uses a magnet to stay in place while drilling. I did receive this drill for free, but I am not going to hold back with the review. In hindsight, I probably should have opted for a punch and die set instead, but this drill worked fine. To hold the tools, the mag drill uses a Weldon type shank, which has two flats in the shaft where the tool shank is inserted. The two set screws keep the tool in place. The fit was extremely tight and there was no play at all. The ways, or the slide that constrains the vertical movement, was not tight enough since the weight of the drill kept falling. I needed to tighten the gib. However, the instructions state that the gib is already pre-tightened at the factory. The gib is adjusted with 3 long set screws that use a jam nut to keep the set screws from loosening over time and over movement. For the first hole, I used a small bit to move the drill into the correct position. Then I switched to a standard hole saw, not an annular cutter. Not a good idea. The annular cutters that I have start at 7/8 of an inch, and I needed a 3/4 inch hole, so I was desperate. Conveniently, the thread of the hole saw matched perfectly with the Weldon shank adapter for the chuck. Compounding this mistake was that I was supposed to have 15 millimeters of metal under the magnet coil. There must be a lot of gearing in this drill to maintain torque because there's a lot of noise produced. Looks like it's going well so far. The hole looks like it's a nice clean hole. Never mind. Now it's time to find some thicker metal in my shop, since I don't have a metal table. Well, that I remembered at the time. I'm getting old. Even though I experienced what just happened, I pushed through and kept using the hole saw, thinking that the extra metal will give me more holding. Spoiler alert, the remaining holes I needed to make came out just fine. It would be nice if the drill came with a plate of steel, so drilling on thin metal is possible. The hole came out a lot better than I was expecting. The drilling did cause a lot of heat, and it fused the slug on the painted surface of the scrap material I was using. With the confidence that this mag drill will be okay for the remaining holes, I arranged the connectors on the panel. The middle bolt is where the shielding will be connected. I made a mistake on a couple of drill locations. The measurements and lines drawn on the panel were correct, but I accidentally added crosshairs to the incorrect line. I needed to make adjustments later, but the outcome was that the motor connectors now have more space between them. If it was too little space, I probably would have caught the error prior to drilling. Now I need to find the correct size tool for these connectors. A 7/8 inch is a hair too small, and a 1 inch is large enough that the two mounting holes for the connector would be too close to the main hole. Fortunately, the rotobroach has the same thread, just like the hole saw, but I can't use it in this configuration because I wouldn't be able to use the point that would help me guide the hole onto the crosshair. To be able to do this, I need to add the chuck. The drill is able to be raised and lowered on the ways to be able to fit the tooling and the chuck and still have some clearance so I can raise and lower the drill. My main fear using the rotobroach with the chuck is that I would have magnified runout, because the chuck could have some runout and then I have this long shank with the rotobroach adding to that runout. But after making the hole, I didn't notice any runout at all, and when I tried to insert the connector into the hole, it didn't fit, so I'm suspecting that the runout is very small. I decided to use the 7/8 inch rotobroach cutter. With the 7/8 inch cutter, I can either enlarge the hole just a tiny bit for the connector, or I can shave off a little bit of material from the connector. I decided to do the latter, and I put the connector in the lathe and just took a couple thousandths off of the outside of that part of the connector. The cut was good, but there's a little lip that is produced, which is normal. Oddly, I noticed less of a lip from the hole saw. These lips are easy enough to remove with the deburring tool, so I'm not really too worried about it. The connector had just enough material to be tightened into the chuck. One of the connectors did get pushed out in the process. Also, the small section of the connector on which the chuck is clamped is slightly flexible, so a good clamping was not possible. I was still able to get all of the connectors to fit though. You can see with the movement of the mag drill, there still wasn't enough strength or force with the magnet due to the small thickness of metal below the magnet. This force was still able to make the holes, but I was on pins and needles the whole time while pushing the drill into the material. I'm using a lift table, which I forgot that I had, which has a metal body, and the metal is thicker than what I was using before. It is still not the recommended thickness of 15 millimeters, but it worked out okay. The astute folks out there will see that I am not using a punch or pilot hole for the pin guidance. I only used the pin to position the drilling at the crosshair I drew on the panel. Later I do create pilot holes to ensure the drilling will not run away from me. In this clip, it is easy to see if there's any visual runout. I'm not seeing any. I may measure the runout at a later date if I see a need to work within a tolerance, but for this job, there is no need. I needed to use progressively larger drills for the small connector holes. I probably should get a stepped drill for this. My life would be so much easier. Here's the final holy panel.
Can I get a amen?
I use a dull twist drill on the holes that have the worst edges. This angle clearly shows the marks left by the base of the drill, but the worst marks, circular in pattern, match the coil of the electromagnet. The magnet gets hot, really, really hot. I learned that if you leave the drill on the surface with the magnet engaged, these marks will happen. If I only have the magnet on during the drilling, no marks are left on the surface. I'm using a 5/16 inch bolt to create a screw terminal for the shielding. I could have used a number 8 screw by itself to serve as a screw terminal, but I think a bolt converted into a screw terminal has a nice professional appearance. I did this on another customer electronics build. The screw only needs to make good contact with the body of the enclosure, which is connected to earth ground. The head of the bolt is faced to flatten the area for good contact with the spade terminal that terminates the shield of the cable. I will then drill and tap for a number 8 screw that will be used to clamp down the spade terminal. This is a board that provides an interface for the inputs of the controller. With this board, you can connect limit switches, proximity switches, or any other on-off type of input. But the voltage of the input device doesn't matter. I'm using this board because the customer is using proximity switches that requires 24 volts to operate. If I was only using the controller, the switches are only able to be connected to 5 volts. That's fine for mechanical switches, but if the switch requires power to operate, then this board is a great addition. I haven't found a good cost-effective large enclosure that includes a fan mount and openings for ventilation, so I needed to create them myself. I decided to create multiple holes for the fan circulation so the customer could add a filter if he wanted to. The holes are just a couple of sized holes placed symmetrically and radially, while still keeping a reasonable structure so the filter can be sandwiched between the fan and the enclosure side. Here's a tip. If you don't have the right size lead to fit into your compass lead holder, 3.9 mechanical pencil leads work. I first started with a hole diameter that matched the distance from the inner circle to the outer circle. Then I chose a hole diameter that fit between the 4 larger holes but still had some space to keep the structure. I decided to make the pilot holes this time, so the rotor broach had guidance and would add some stability to keep me from being on pins and needles. I figured this would be a good idea since I only had the thin side of the enclosure as the metal for the electromagnet. The drill did come with 2 annular cutters. However, they were both the same size, not sure why, and they were too big for this application. Still, I think the drill is a good value for what you get, even if the annular cutters had not been included. Also, the annular cutters that were included did have a pin as well. On the bottom of the enclosure, I drilled ventilation entry holes. I intended the airflow to travel from these ventilation holes and out where the fan is located if a filter is not used at the fan location, since these vent holes are underneath the base for the electronics. If a filter is used with the fan, I suggest rotating the fan and allowing the air to enter at that location so there is a positive pressure inside the enclosure keeping dust and debris out. Now I'm locating the holes where the spindle cable and VFD, variable frequency drive, power cord will enter the enclosure. I'm using an M18 cable strain relief bulkhead nut for these cables. My use of this hole saw at the beginning of the video completely wore the teeth and did not want to bore anymore. I went with the twist drill as an alternative since my rotor broaches were too big for the M18 major thread diameter. You can see how the large twist drill caused an oscillation with the mag drill base. There just wasn't enough metal below the mag drill to keep the base sturdy, but the holes worked out anyway. All of the connectors were added to the removable panel, and the cables and wires were soldered to these connectors. There were 61 solder points connecting the cables to the connectors. Most of the solder points were very small cups. This took quite a bit of time to do. I think the soldering of the cables, which were 48 for the encoders, 32 for the motor cables, and then 61 for the connectors, totaling 141 solder points for the entire build, probably took the longest of any part of the build. I'm not sure which one is more tedious though, the cables or the connectors, with those tiny little cups. The cables now need to be connected to the drivers and the controller input board. I added 3 M18 cable strain relief nuts to the removable panel. One for the main power cord, which I'm hooking up now, one for the e-stop cable and button, and one extra for whatever the customer needs. Front page. I hired this out. Here I am connecting the two main systems' protective earth ground to the enclosure, the VFD and the power supplies. To ensure that the power supplies function properly, I'm going to test their DC output. I do this with the drivers disconnected to make sure that the drivers are safe, just in case the power supply outputs a voltage that is not expected. This test is to make sure there is continuity between the shield terminals and the ground of the enclosure. Unless the customer asks for the e-stop button to be mounted on the box, I typically provide it as a cable and button so that the customer can mount the button where it is most accessible. The box isn't usually positioned where there is easy access, and the e-stop button should be positioned where you can hit the button fast, just in case there is a dangerous situation happening or the machine is causing damage to itself or the workpiece. This machine will be slaved between the Y-axis and the A-axis. The two motors on the right should move at the same rate. A couple of things need to happen for this to be a success. First, both of the drivers, the A and the Y, need to be set at the same amps and microsteps. Second, the steps per unit, velocity, and acceleration need to be set the same in the motor tuning section of the control software. Now I'm testing the proximity switches and the connection to the controller and the input board. A really nice feature of this input board is that there are LEDs to indicate each input. The LED will tell you if the proximity switch or limit switch is engaged or not. Now for the final wiring and test for this electronics assembly, the VFD power and the VFD to spindle cable. I was not looking forward to the test, however. Remember the spindle collet nut was jammed on at an angle? I still needed to test it, but I didn't want to keep the spindle on for more than a fraction of a second in fear that there would be either an imbalance that could cause some damage to the spindle, or that the nut would fly off and cause me damage. I hope you enjoyed this video. Please leave me a comment, click the like button if you liked watching this video, and subscribe for more of this. Thanks for watching.